think, shall we wait for 5 more minutes for people to join in, or?
Yeah, I guess you could wait, but I started recording anyway.
Okay.
Are you not able to see the comments? Why?
Oh, I did not open the chat, I guess.
No, it's over here only. Like the no, not here. When you click on, yeah, it's not showing the chart option for you for some reason.
Yeah. Okay.
I don't know why that is the case. Usually on the browser, it should work.
Okay. I am on the browser only, but for some reason I'm not able to see.
Yeah.
No.
Okay, then I'm leaving.
Yeah, cool. Hey everyone. I think we'll just wait till 3:05 for people to join in, and after that we'll start. So can I know some statistics? How many of you attended any robotics classes previously? Hello? Can anybody hear me? Or like,
So what do you mean by robotics classes?
like advances in robotics or mobile robotics or any other robotics courses in our college? Control theory.
Can you just at least because we're all in second year going to that, so you have more chances to take.
I'm really not able to hear you. Your voice is very muffled.
We are all in second year, so I guess none of us has
Okay.
attended any robotics courses.
Okay, cool. Yeah. Fine. So yeah, it's 3:05. I think we'll just start from now and let others join. Um, And also just let me know if I'm not making sense to you people at any point of time, because this might be a little bit convoluted. So let's start with what is motion planning first off. So let us say that uh, you know you sort of want to launch a satellite. Okay. So now you will have to decide an orbit, right? Something like this, and any other orbit, and you want to launch a satellite. So also everybody, please be interactive, and you can talk at any point of time, or else I cannot deliver one-way lectures. It will be pretty boring even for me. So if you have any question, or if I'm not making sense at any point of time, like the new PS5, you can just tell me. So yeah, let's return to the point. So okay, so now we are in some orbit, and you need to maintain this orbit, right? So let's say there is a small satellite here. At every point, so at every frequent intervals, the satellite has to constantly keep moving around the Earth so that it will not fall into the gravity of the Earth, right? So it has some few thrusters, and from the thrusters, it just emits some sort of a little gas or whatsoever to keep its orbit, right? So this thruster, you call that as an actuation or a control. So this actually gives the satellite the freedom to control itself in this whole trajectory. But the major point of a control engineer is perhaps first of deciding this orbit in the first place, and second of keeping this trajectory in the first place. Now, this is one part of control engineering. Okay, now let's come to roads. We have a car over here and some other car, whatever. Um, let's say this is a two-lane road, and let's say this is our car. Okay, so our car has an onboard uh, vision sensor. So it's some sort of camera and some lidar. It will get inputs from the lidar, and so your major task is to first off move in this traffic without colliding anybody else. So what will the vision people give you? The vision people will give you this lane boundary, right? They'll tell you what is the width of this lane, and where all these cars are, what are their widths. They'll give you a bounding box, sort of something like this. With the help of lidar and vision, they'll tell you what's the exact distance, at what velocity is this moving. So note from this point on that I'll denote velocities by vectors and arrows like this. Okay. So how fast this velocity, the other vehicle is moving, and in which direction it's moving. So this is all a part of pose estimation. But now, where does the point of a motion planning person come? Okay, let me just clear these things. Okay. So where does the motion planning person come? So once he gets all of those things, let's say there are the obstacles here, and this is your view. And now somebody is going to give you something called a waypoint. That is, these are global points leading to some goal. It may be your home or a shop or whatever. And now, the thing you have to do is that you have to follow these global points as closely as possible without hitting any of them, and keeping track of something called a reference trajectory. So this is your reference trajectory. I think I'll draw that in some other color. Yeah, cool. I think so. This is your very bad. So this is your reference trajectory. You have to keep as close to the reference trajectory as possible and avoid all those vehicles. Okay. So And there are many places where control engineering shows up, and majority of motion planning is entirely controlled. So what I will be teaching you in this short duration is, I hope I will get through trajectory generation and how to avoid the collision first of all, and I'll give you a brief intro into what exactly is optimal control. So how do you decide that you've seen the satellite, right? How do you decide that how much thrust it should put out? What's the force it should put out to stay in this orbit? And with respect to a car, then what what is the steering angle it should take? Okay, and with what velocity it should move forward. So these are all the things that you will be learning. If it if it wants to reach a goal, what v and omega it should take. So these are all the things you will learn in this little duration. And at any point of time, if I'm not making sense, uh, just let me know, because even now I'm not getting much of feedback. So just stop and let me know. Good. Let's proceed to the next one. Okay. So I'll probably ask you a little question right now. So you can see that this top row and bottom row, there are two different kind of robots. Can you tell me something which differentiates a car and a BB-8? Both of them move on the ground. Is there something very unique between both of them? Just say yes or no if you cannot decide or figure out anything. Okay, nobody is listening or what? Cool. So if you can see this robot, it can actually move in every other direction, right? It can move this way, this way, this way, and this way. But a car, you see, it cannot move sideways. So a car cannot move sideways, right? It cannot slip. But BB-8 can slip. And let's see this thing. This robotic arm also has something called singular points. That means at some point of time, this robotic arm cannot move beyond a point because of its configuration. Whereas a drone, again, it has a free move over the entire space, right? Uh, so, so basically, this second row, these robots, which can reach to any state in the free space, are called holonomic robots, because they're not constrained fundamentally in their construction, so that they can take any direction and any velocity and move in any side. That is, they can go to any configuration and also return to the same configuration in the same way which they went. But let's say a car, if it goes this way, the only possible way it went is that it can go like this. But again, for it to come back, it cannot take any other direction. Like, it cannot come back like this. But this robot, if it goes to any position, it can come back from any other direction also. Oh, I think I missed in the first point. So this thing can reach the same state from many other states, while this thing cannot. I hope that corrects it. So, okay. So right now we'll see what is the goal of trajectory generation. So let us say there is some initial. So usually it is like this. Okay. So what people will ask you to do is that you will have an entire GPS coordinates to you, and somebody will ask you to move from this point to this point, and they'll give you some time. Let's say they'll say 10 seconds to reach this point. Okay, and now your fundamental problem is that how do you reach to this point? The problem is, if this point is like this, a car can easily go straight like this. right? But if this point is somewhere here, but now a car cannot execute this trajectory, right? It cannot go straight. It has to take a turn somewhere. So you need to decide a trajectory which will take this car to this place. And that trajectory, whatever you decide, finally, it should be executable by the vehicle uh, that is intended to move from this point to this point. So fundamentally, we'll be dealing right now with non-holonomic trajectory generation. So non-holonomic robot means a car, or we have a small robot in the lab. I don't know if you saw it. It's called a Husky. Even Husky is a non-holonomic robot with a differential type. So they all cannot take, uh, you know, sideways. They cannot go sideways like this. It's not possible for them. They can only go like this, and they can curve like this. Cool. So let's recollect.
Sir,
Yeah.
is it easier to generate trajectories for non-holonomic robots or holonomic robots?
Holonomic robots per se don't require any trajectory. They can move. They can have free, what do you say, free movement. Let's say there is a drone, so it can at any point of time, it's capable of taking sudden movements. So now let's say there is a let me just sort of clear this thing. Okay. Okay. So now let's say this is your drone, and there are some obstacles like this. Okay, and you need to reach this point. A drone, let's say you came here and you spotted this obstacle just now. Okay, just now. So what the drone can do is that it can immediately take a turn like this, and it can go like this. So somebody can give you an initial trajectory which goes along this collision free space, but you can solve it on the go too. It doesn't exactly require an initial trajectory. It requires a proper control. That is, you need to control such that it doesn't collide with anything. But if you take non-holonomic robots, on the other hand, if you come here and if you suddenly see this, there is a potent chance of collision. So it's better that you have a trajectory beforehand. And obviously, it is harder to decide for a trajectory for a non-holonomic vehicle. I'll tell you why. Than for this other vehicles. So let us say we have this small cube, okay, and now there are a few obstacles like this, okay, and let us say this is your vehicle, and you want to go to this place. Fine. So there are many routes here. Okay, you can see that this is one route. You can see that this is one route. And obviously, because it's a non-holonomic robot, it has something called a car constraint. Like a car or anything, it has to go on a small circle because it cannot slip. Okay. So, but you see the point, right? Why is this trajectory hard? If the robot comes here at some orientation like this, say like this, it hits this thing, right? First off, because the robot is not, what do you say, uh, symmetric in shape, something like a circle. It can turn, right? So if it turns, there are several configurations for it. You need to decide a trajectory for every other configuration in which it can turn, right? So you need to see through that this robot is at a particular orientation, at a pose, at this point, and it is following this trajectory strictly. Or else what will happen is that uh, it will eventually go and collide this thing. So if you want to avoid all of these things, it is best that you decide a trajectory beforehand and execute it in a static scenario like this. We'll also see what will happen in dynamic scenarios, but I'm just telling. So what do people usually do? They actually say that, okay, you're starting from this point. And now where do you need to go? they say that there is an algorithm called RRT. So what RRT does is that everything in this space, every point in this space is a configuration. So you'll say, at this point, this is some X. X means, okay, from now on, I'll represent capital X as some X comma Y, some position, okay, and some orientation theta, okay. So at every point, what RRT does is that it sees the orientation. So at this point, the robot has to be this way, and so on, and it sees the most feasible orientations, and you have to take it. See, at this point, if you take a wrong orientation, what will happen is that you will not be in the free configuration space. That is, sorry, free space in the configuration space. So CS is the configuration space, meaning set of all poses and positions. So this is existing at every point. So usually, because we cannot do that, we'll sort of divide this world into a grid and try to do our best. So CS is the configuration space, and we'll say CO is the obstacle configuration space. Just remember these things, because I have not written these things in this PPT, and you'll have to just get used to the notation. Cool. So, did you understand why it is harder?
Yeah, thank you. Like basically,
Yeah.
like with cars and other like a robot, there's like you can't explore all of its immediate space and move in real time. So you need to have it done beforehand so that it avoids all these obstacles.
Right. Yeah. That's so. Okay. So, what is the problem of trajectory generation? Is that now you have to go from some point x naught y naught to some point x of y given by the user on some GPS or something, even on a Cartesian plane. And now you can see that there are several such paths, but the path selected, and also you have to adhere to some user imposed constraints. So what is the user imposed constraint that we have seen previously is that that whenever the user gave so and so path, he said reach by some t equal to 10 seconds, right? So that's the user imposed constraint. And you can also see sometimes the user may give some constraint like this. At this point, maintain some velocity that is 2 meters per second in the x direction and some 3 meters per second in the y direction at this particular point. Okay, so at some x tc and ytc. So these are all user imposed constraints. They give you these constraints for whatsoever reasons, and you have to get a trajectory for those constraints. Fine. We'll see one very good method and easy method probably to generate a trajectory. Initially, what we will do is that consider the robot in a 2D configuration space. Okay, so what we do is that this is a 2D configuration space. That is, it's a plane. We are neglecting any height of the robot or whatever, and we'll only consider x, y coordinates. And okay, so now we'll just get to some good notation. We'll represent Q as the configuration or state of a robot. So what we'll say is that Q is x, y, the position, and some theta. I think I just previously wrote something else for it. Just remember this thing for these slides from now on, because I wrote it with Q. Cool. So yes.
So in this scenario, do we have like dynamic objects like other cars that are moving, and is this like a pre-mapped area that we are finding a trajectory on?
This is a very static space. That is, this is a pre-mapped, what do you say? It's a static space. So this trajectory is pre-decided that avoids all these obstacles. So we'll see how to extend these things to dynamic things also. That is, if this thing suddenly starts moving for whatever reason. So we'll see that later. But now this is a very static space, and we need to generate this trajectory. Okay. So we'll go to the next point. So these are so T naught is the initial time, and TF is the final time. Okay. And TC is some time in between. Like let's say here at t equal to 5, let's say, I say that you have to be. I say that you have to be at some position, let's say 5 comma 6. Okay. So I say at t equal to 5, you be at a certain position 5 comma 6 at certain heading angle, let's say some 40 degrees or whatever with respect to the x-axis. So you need to find a trajectory which satisfies all of these constraints. So there are several such functions, right? What we will, and we don't know. Okay, what is a trajectory? First off, just forgive me, I forgot to define that. So trajectory is an evolution of the state space of the robot. So what it says is that q of t is what you have to find. That is, how does x vary with respect to time, and y vary with respect to time, and how theta varies with respect to time. With respect to time, also what's that? Respecting the constraints given by the user. So you need to find these functions. And also, let us see one fundamental thing with non-holonomic robots. So non-holonomic robot cannot slip. That is, it will always go in a straight line like this. Not straight line, on a fixed direction. So if you are giving some theta, now it will always go on this theta. So how do you decide this constraint? How do you decide theta? Is that you have some expression for any parametric curve. If you find dy by dt by dx by dt, that is a variation of x-axis, x coordinate and y coordinate with respect to each other, it will give you something called the slope or the fixed direction in which this is going. Okay, so basically this is the constraint. So what you're saying is that Vy is actually equal to Vx tan theta. Okay. So that is the constraint that you have to respect for a non-holonomic robot. Okay. Now what we'll do? Okay. And there is something else that we forgot, because this robot actually moves on this curve. So there is something called an angular velocity. Curve can be seen as little pieces of circular motion. Just it will have some angular velocity at every point of time. That is omega t. Okay. So what we'll do is that we'll represent q dot like this from now on. X dot, y dot, theta dot, cos theta, sin theta. You can see this thing, right? It's pretty apparent. Cos theta, sin theta, and 0, 0, 1. That is your braking velocity, the velocity, like let's say 5 meters per second. If somebody says you, then you have to go on a fixed direction. What do? You break it into x component, that is x, vx cos theta, and vy sin theta. So that's why you get cos theta, sin theta 0 and 0, 0, 1. So we'll go to the next. Okay. So now that you have your state space representation of your robot, so what do you have to do? You got the constraints, you got the user given constraints, you got the robot's inherent constraint, that is the non-holonomic constraints, and also you have some fixed time or set of points that you want to pass through. Okay, and there are several such functions, right? satisfying those things. So this is a function. So this is a function. This is a function, and you need to find the function which best fits this thing. So there are various ways to get a function which actually best fits. There is something called variational calculus, which is completely, what do you say, dedicated to finding a function like this. But what we will do is that we'll assume there is some function. Hopefully, there is some function like this, which respects the given constraints, and we'll represent this function with something called a Bernstein basis. So, what is the Bernstein basis? Basically, this is a Bernstein basis. So, you are representing the function f of x, okay, and this f of x is a function which changes with respect to time and space, x, t. So, and you will choose some degree to this Bernstein. Let's say I am representing until 5th degree, then I'll say n equal to 5. And I'll write, this is NCR, the standard combinatorial symbol. And t is the time variable, which is actually going from 0 to 1 in this place. Okay. So you represent the function with a time domain 0 to 1, the function f of x with some basis functions. That is, these are the basis functions: ci, ti, 1 minus ti whole power n minus 1. So those are the basis functions for this function. So what we'll do is that we'll initially parameterize xt, that is, this curve is there, right? So we'll make a parametric representation. We'll get xt and yt separately, and also theta t separately, right? So now we'll have a parametric representation of this whole thing. Okay, cool. So what we'll do is that, so this is bi. Basically, bi is this. Bi of mu t is actually ci 1 minus mu whole power I. These are the basis functions, Bernstein basis. And mu t is actually a normalized bit like this. So if the user has given you some t naught and some tf, so basically because these bases are defined in between, or no, basically because it's a standard to define your trajectory with the time varying between 0 to 1. It's a pretty much control theory standard. So what we'll do is that we'll just normalize our time. How we'll normalize it is that we'll say t minus t naught by tf minus t naught. So you can see this will always be between 0 to 1. Okay. This is your new time, t dash. Okay. So this is how you parameterize the time. So you got this mu t, and now you have represented the basis. Let me just go back and show you. So you see, right? So now you have represented xt as a parametric function, and also you have built that function with a Bernstein basis. Similarly, you will represent tan theta as a parametric function with Bernstein basis, bi. It's better that you people practice these things on a paper, so that you'll understand better how the mechanics of these things, how the mechanics of this math works, or else it will be a little bit difficult to directly see what is happening sometimes. Cool. So now what do we know about yt? So what do we know about y dot? Y dot is actually equal to x dot tan theta. So we'll represent y as the integral of this thing. So let's integrate it. You will get an particular integral plus some constant. Why not? Okay. So once you get those things, once you represent things like that, you have a parametric representation for xt, yt, and tan of theta t. So far, is everything good? Is everything okay? Is everybody understanding? Or hello? Hello? Is anybody there? Hello?
We can hear you, sir. Yeah, we're here.
Okay. Because sometimes my internet also randomly just gets cut. So just let me know when I say hello. It's very
Sir.
crazy here. And it's,
Repeat what that function B is trying to do.
okay, cool. So now you have the parametric representation of x, y, and t. Great. So now what we do is that we have some initial conditions. The initial conditions the user has given to you is that at t naught, let's say he asks you to be at 0, 0. So you have this initial condition. So you'll say x of t naught is actually 0, and so is y at t naught, and xtf also he gives something like that. And there is some good thing with this constant representation is that you see at t naught, you see that this mu t is actually equal to 1, right? Sorry, 0. So at t naught, this is actually 0. So then you will get a very good direct condition on W naught. Okay, let me just. Yeah, I think it's 1, not 0. Yeah, cool. Yeah. So these are the Bernstein coefficients at some time intervals. At some t equal to t naught, you can see that only b naught exists. So b naught is actually 1, and this is a 5th degree Bernstein. Okay. So rest of the things are 1, 2, 3, 4, 5. They are all 0. And at T5 and TF, what happens is that only the 5th degree basis exists. So you can directly infer W x naught and W y naught. How? Because xt naught is actually this whole expression, and rest of the things are 0. You will get W x naught is actually equal to xt naught, right? Similarly, for you get Wx5 as this thing because rest of the things are 0. So now what you have is that you have a set of linear equations, right? Those equations, linear system of equations, those equations exist at the time intervals which the user has given. Let's say some tc. I'm only taking one time interval, but you can take any time interval, any number of time intervals as you wish. So let's say at tc, you have several other coordinates, and at those point of time, you need to find these weights, right? So what we do is that we have brought this equation into form ax plus b. That is, so basically this is the whole thing. And you can actually see that this is, it can easily brought into a matrix format. W times b is equal to x. So that is what you did here. And you'll get this linear system of equations. Once you get this linear system of equations, just keep it aside for a moment. And now let us go to, once you get this linear system of equations, take the pseudo inverse and solve for Wx1, x2, x4. You already have Wx0 and Wx5 with you. So you get all the Wx1, x2, x3, x4 subject to the standard linear algebra things, that is the system over constrained or under constrained. You can give many number of constraints, so or the user can give as many number of constraints. So almost the problem is entirely in your hands. So make a good proper rank matrix, and you'll easily get good set of weights W1, W2, etc. for the conditions which you gave. But the tricky part is that, because we have this non-holonomic constraint, that is, which says y is actually x dot tan theta, and it has an integral in it. So what we actually do is that, because our good point is that we have some T0 and TF. So we will actually do some numerical integration, and then we will get it into a form like this. WK1 F1. F1 is actually a function where from T0 to T, you can expand T0 to T with any rule, Simpson's rule or whatever favorite rule of yours, trapezoidal or whatever. You can just expand it between T0 to TF, and you will get this integral in terms of T. So now you have F0 at T and F1 at T and so on, and WK0, K1, etc. Okay. And for tan theta, you have the same thing like x and yt, and you get a parametric curve for tan theta. So now you see the point, right? You have gotten these coefficients of this thing, and you need to find w, k1, k2, k3, and so on. So again, you will do the same thing. You will just bring them into a linear system of equations form and solve w, k1, k2, k3, and k4. And finally, you will get all the set of weights for this question. I mean, this problem. So now what I want you to do is that actually I'm thinking, because there's a lot of content to take in. So initially I thought I'll teach planning under uncertainty, etc., but it's too heavy as far as I see. So what I'll do is that I'll give you some very basic assignments. You don't even have to take some Bernstein polynomial or something. Just take this curve, okay? A t cube plus b t square plus c t plus t. And similarly for y, you take that thing. And also for theta, no, don't take theta. Right now you just take this thing and consider this as a holonomic robot, okay? Now I am just asking you to solve this problem on yourself at home and with these constraints. So what I'm saying is that the constraints at T0 are X, 0, 0, and TF are 8 and 7, and at T4 are 4 and 3. You can change these numbers any way you want. And this thing for Vy and Vx are also given the constraints. I wanted 0 for you to be Vx equal to 0 and Vy to be 0. And similarly, I mean, same, you can follow this question, this PDF presentation or whatever. And I want you to find A, B, C, D, E, F, G, H. And later on, if you have successfully found this thing, take the curve, take a parametric equation for theta t, the same third degree polynomial, and give your favorite constraint. Give some constraint at tan theta equal to some value at some point, or like theta t is 40 degrees at some t4 or 5, and solve for it. And we'll see how to evaluate the assignment. Okay, so that concludes the trajectory generation part. So now you have gotten a trajectory for x of t, y of t, and theta of t, and you can execute this thing for a non-holonomic robot model. Are there any questions so far? It's already 4 o'clock, quarter to. Okay. Looks like there are no questions. We'll just proceed to the next part. So far you have seen how to generate a trajectory when there are static obstacles with a given set of coordinates. But now what we'll do is that we'll actually see if there are, let's say there are two robots like this, and one is moving this way and other is moving this. Let's call them A and B. So the thing right now, what we want to do is that, are they both going to collide in the future? Okay, so I think there's a figure here. Okay, so we'll see that there is RA is the radius. These are all circular robots. Okay, so RA is the radius for the first robot, and RB is the radius for the second robot, and each of them are at a position PA and PB, and one is flowing with the velocity VA, and other is flowing with the velocity VB. So the first question is, would they collide? Can anyone give a simple collision check or something? How do you know they would collide in future? If their trajectories intersect, would they collide? Probably not, because they might reach at a different time, right? So we need to come up with some good constraint. So what we will do is that we'll actually do this thing. So we will shrink this robot into a small dot and take something called the Minkowski sum of these two robots. When you take the Minkowski sum of these two robots, what you get is a very big disk of some combined radius capital R equal to RA plus RB. Okay, and let's say we are solving for this robot's um velocities that might collide. So what we'll do is that we'll try to observe everything from our reference frame. We call that egocentric. So what we do is that if this is VB and that is VA, so we take the relative velocity vector, some VAB, okay, that is VA minus VB. Once you take this relative velocity vector, you see that from this point on, if you draw a line, so how this thing actually works is that you solve it every instant. So let us say you are at some t equal to t something a. So at t equal to ta, even though this robot is moving, how would you calculate you're about to collide that robot or not? Is that you will actually freeze the whole time, and then you will increase its radius by capital R, and you will see in future if you are actually falling into this disk, if you are going along that radius, along that velocity direction. So that is how you will see if you're actually going and colliding into that robot. You can easily check that by drawing a straight line like this. So P into T plus some PB is actually the equation of that straight line. So this should not be falling into that disk, right? Represented by PA with some radius capital R. So this is the condition that at the future you should not fall into this thing. You can once you understand that, what you need to do is that now you know whether you're going to collide or not with a given velocity, some VB. Now what you need to do is that you have to select a velocity which will actually fall out of this disk, right? Or else at this instant, in future, if this robot is here, you are going to collide. So what we are going to do is that at every instant, as frequently as possible. So for every delta t equal to some 0.001 or whatever seconds, we are going to plan our, our thing. What happened? So yeah, this is basically the condition that in future you should not fall into the disk. He has taken this is from wiki. Yeah, it's the same thing. It boils down to the same thing. So what you understand from this is that this is VO. VO is the geometric representation of all the velocities that will eventually result in collision. The dynamic obstacle contains the current observed velocity. Okay, so now you need to find a velocity which will come out of this disk. How do you find that? So basically, your main thing is that you need to first, what you have to do is that you have to go into the velocity obstacle space. That is, now you see this is actually the Cartesian space where the uh, is actually represented in x and y, but we are doing all our calculations in something called the velocity obstacle space, where you know uh, where the entire thing is set of velocities, and we are going to test if our velocity falls within a certain disk of radius RA and RB. So this is the disk with capital R, the enlarged radius of robot 2, and now this is at some fixed instant of time. Now what we do is that we need to find this velocity which will come out of this disk, right? How do you do? How do you do that is, you can actually observe that for this circle, this tangent actually makes an angle of 90 degrees here, right? So basically this is a right angle triangle. And so from there, now this is small r is the vector from x1, y1 to x2, y2. That is the current position of the robot. And this is capital R, the radius, and this is v12. But then how do you get this length? Is that you will just project this, this v12 onto R, and sorry, this R onto v12, and see the length it takes. How do you do that? Is that you just take the dot product and you will get it. After you do that with just the right angle, what's that, Pythagoras theorem, you will get this equation. So whatever velocity you take, the relative velocity should be greater than or equal to r square, or else what happens is that it just falls inside the disk and you will be colliding with that robot. Is this thing clear, or does it require any explanation?
Sir, for the velocity to check whether it's inside the cone, can't we just check whether the angle that the relative velocity makes lies within the cone? Like we know the
Yes.
starting point of the velocity, right? And we know the
Yeah, right.
angle, like we know the angle that it makes. So can't we just check whether it lies within the two tangents?
Yeah, that's exactly what you're checking right here. So what you are checking here is that you're checking if you are falling within these two tangents, right? So what you're doing is that this is the extreme tangent and this is the extreme tangent, and this is the capital radius R. What you said is exactly true. You are checking if whether you're falling into this thing, into this thing. Maybe you can do that calculation in some other way. Maybe possible. I'm not denying, but doing this way is better. Why? I'll tell you. The way which you have said is also done by Das Gupta. Uh, Yeah, so you can see his paper, Das Gupta's paper. He's from IISc. He did it in the way which you said, and that thing turns out to be pretty complicated. So what we will do is that we'll take. I hope I got the author's name correct. Else I'll forward you the paper. So what we will do is that we'll just come up with this simpler equation, okay, to see if we are actually in lying between those two tangents. Any other question? Okay, cool. Fine. That's a good question, actually. Fine. So now, after we get this equation, yeah. So what do you see? R kept the small r as r is actually x2 minus x1 and y2 minus y1, and v12 again is relative velocity with a similar expression, some v1 minus v2 minus v1 is v12. So when you expand that equation, you get this equation. This is Fi. So this is the fundamental equation with which probably you'll be building your entire thing in the initial days. This equation is called the collision cone. So whenever the value of collision cone, what did we represent as? Okay, is greater than, is less than, you will collide. So you always need this value to be greater than or equal to 0 to not collide, right? That is your fundamental problem now. Make the value of collision cone greater than 0. So that you won't collide in the future. That is, your velocity won't lie in between those two tangents. Cool. So now what we do is that there is a very simple method that actually allows you to solve this very complicated equation in closed form. See, here you can also solve, but you see there are several choices for x dot tc. X dot tc is just the x, what you call x component of the velocity for the other robot. So you will actually sample and you will solve maybe, but that's a very tedious process because there may be several options to sample. Particularly, it gets complicated when there are other constraints given. So what we do is that we do something called scaling. Scaling is a very simple process which allows you to get a closed form expression of this collision cone. So what you do is that you just multiply this component of the velocity with some factor called S. So you see x and y components are actually multiplied with some factor called S. This is actually the scale. So what will scale do is that, let's say this is the velocity. If you multiply with a scale greater than 1, you will increase the velocity. If you multiply with a scale less than 1, you will reduce the velocity. But there is a issue in this formulation. I mean, I won't say it's an issue, but you can see it's a constraint, is what I'll say. Because why? Because you see here, if you decide a scale, no matter what it is, you're always going in the same direction, right? That is, you will only slow down or speed up to avoid collision. That is, you will either go fast and pass before that obstacle, or you will go slow and let this obstacle pass. So this is the one constraint that scaling imposes, but it will give you expression in a closed form expression. How we'll see. So this is the concept of scaling. I hope you got it. So what we do is that basically you see scaling fundamentally means that, let's say there is some point x and y here. So let's say with some velocity v initial, you are reaching this point at some time t. When you do some scale s into v, you will have to reach the same point t at some other time. Some other time t naught. You'll reach the same point at some other time t dash, right? So what you do is that it's just a transformation of time in the parametric equation that you got. So that, let's say that the transformation is actually Tn, that new time you arrive at this point T dash, which I written here. It's actually Tn here. So the velocity at Tn is actually a multiple of the, this there should be here dot here, x dot. Okay, it's actually a multiple of scale times the multiple of the velocity at that position previously. So once you understand that, so this entire equation, if you solve, you can actually bring it into this format: a square plus bs plus c, where a and b and c are actually what? Are actually functions of x and y, right? And v dot, I mean vx of the other robot. So, and vy of the entire variables vx, vy, x, y, t, and vx obstacle and vy obstacle. So ABC are actually a function of that, and you can bring that into this form: a square plus b. So once you get this into this format, a square plus bs plus c, so now the problem has become very simple. You don't have to sample or do anything. This is just a, this equation has two roots. Let's just say it will look like this. So let us say a square plus bs plus c. How does it look? It looks like this or like this. So this is fi, right? This is the collision cone. You're drawing it. You need to select all those values which are greater than 0. That is, if you stay this side, you're always greater than 0, right? So you're staying on the side which is always greater than 0. Here you're staying on this side so that it's always greater than 0. And how do you get these 2 points? These 2 points are just the roots of that equation, right? A square plus bs plus c. The roots of that equation are basically minus b plus or minus whatever. And you just check the condition and you just get a scale. And now you will speed up or slow down. And actually, so what I'm thinking is that what you have to do is that you have to expand these equations by hand and get it into this format, a square plus bs plus c, and solve for s. That is your assignment. And for any configuration, your favorite configuration, take like this. Ensure that they meet at some point and they collide, and you need to avoid the collision. I'll show you a little bit of demo. Okay. So all these robots are actually moving by scaling. So without any scale, they would have actually, all three of them would have actually collided. But now you see they are only grazing and they are going. That they found a scale which had them merged into such a tight space. Let me show one easier. Yeah, good. So you see, right, with scale, the only thing is that they found a scale which let them slow down on some trajectory and move. So that is basically your assignment. You will have to implement scaling like this. You can submit the assignments whenever you want. So this, but I'm just giving you an idea. No, I'm just giving you a problem so that you'll get an idea of what this entire setup of motion planning is. There are several components. Now comes the major part that you have found out a trajectory, you have found out a velocity which takes you out of collision. So now let us say that you have been asked to you have been asked to move like this on this trajectory, and suddenly this robot started moving, right? Suddenly there are two people coming like this, and you fixed up on a trajectory. You will keep moving on this trajectory, but now what's the problem? You will have to avoid these two people. So now you see that there are two components which are getting overlaid. First component is that you actually get a reference trajectory, and second component is that you'll actually have to do collision avoidance. And the most important part also is that after you do the collision avoidance or whatever local behavior that you have to exhibit, you will have to come back again to the global trajectory. These are all what a controller will do. It will perform all these operations. So now we'll actually look into optimal control. So far, what have we seen? Just let me know if you people are getting bored or something, so we can see if we can conclude, or if for doubt clarification or something. Is everything good so far? Hello.
Hello. So even without the scaling the obstacles, as in the robots will avoid the obstacles, right? So if
Uh,
I don't use scaling, then also they'll like avoid the obstacles.
and I mean, I don't get you. So if there is an imminent collision, you will
Yeah.
have to select a velocity which is coming out of the collision, right? So let us say you are going.
So what if I minimize the distance from the like actual trajectory to the velocity, like the minimum distance from the cone
Yeah,
and
how do you
the
get that velocity that to which you want to minimize to?
yeah, so like we have the trajectory planned right from before.
Yes, but even then, yeah, that's also a method. I'm not denying it. So, see, these are then again you'll have to take several trajectories. But if your goal is to go on a fixed trajectory, let's say there is this fixed trajectory, okay, and there is a robot which is coming this way, and let us say t equal to 5 seconds, you and the robot are both going to be here. So you have to select a velocity which will keep you on this trajectory, right? That you have to keep the trajectory for some reason, whatever reason it is. I mean, let's say the trajectory is actually a track for a mobile robot in a warehouse. They should not cross their tracks because they will go and collide into other things. Let's say it's a track. What will you do? You cannot sample trajectories like this. I mean, you cannot build new trajectories like this and do it. So this is for a particular case. It works when you have a fixed trajectory and you want to avoid collisions. Any other questions? Okay, cool. Uh, so what we will do right now is that we'll try to do what she says. That we will probably try to deviate from our trajectory a little bit and go to a goal. Uh, yes, because sometimes it might so happen that the robot is free to move, and that is the control problem. But most of the times you will see that scaling is a very interesting situation because let's say you want to build some sort of a traffic simulation, and you have to keep your trajectory. Let's say you want to go from you want to overtake this robot from this point to this point. In a road sort of situation, it is very hard to plan reactively every instant. It is better if we have a trajectory and if we evaluate safety on this trajectory beforehand. But what we will do is that if we forget about safety and if we can safely overtake this robot, you can see that scaling is a very good option because scale will give you some value to overtake this robot and go to your desired location. Cool. So what we'll do right now is that what did the people do so far? So they gave you a starting point and a final point, and they ask you to follow a trajectory, or they ask you to follow some, or they might also ask you to not follow, keep close to some fixed set of points called the global waypoints. So either you try to follow them exactly how they are, that is, you try to pass through them, or in some unforeseen circumstances, if there is something else which is coming like this, you can slightly deviate but still be close to this thing. So this is where both collision avoidance and this thing come hand in hand. Uh, so So what we do is that basically we formulate something called a cost function. A cost function can be very simple. Let us say you want to reach your goal. So basically this is your starting point, let's say x naught, and this is your goal xg. And if you want to formulate a simple cost function for this problem, xg minus x naught should be equal to, sorry, you need to minimize this cost as you go, right? That is, you want to get to the goal as close as possible while following some certain constraints. That constraint is called a motion model. You have seen for drones that this is just a what do you say? It doesn't have any constraints whatsoever. But a non-holonomic mobile robot will actually have some constraints, and it actually has something called motion model. Uh, Even this thing has, but I'll just write this one. So how do you calculate xt plus 1 is that you'll actually say it is xt plus some vx cos theta t, right? So you're following in the direction of um, vx cos theta. This theta t is this way, not that way. So at previous instant, theta t in times delta t. So this is how this is called a motion model. That is, you'll reach the next state with the current input, that is the control, Vx and some theta, like this. This is a constraint because this is the only possible way that you can move. And let's see for this. For this, there is no cos theta term. There is only Vx delta t. So Vx delta t plus the current position xt. So this is the motion model, and this is the new position x new that you reach at time instant t plus 1. So, and any other constraints which the user will impose. So what do we have so far? Fundamentally, we have a cost function. We are calling it fy. This cost function can be over the entire state space. So y is the state space. State space basically for us is x and u. U are the controls, that is Vx, Vy, omega, whatever you decide to. And X is the position of the robot. So Y is a vector which actually is composed of X and U, the state, and such that some Fy is equal to 0. That Fy you can actually see is the motion model like this. This is the Fy. So you have to minimize this thing. So this is the basic optimal control problem. How do you solve it? Let me take a document. It's far easier to show. So what you basically do is that you will actually transform this constraint into something like this. Let's say you have been given some xt plus 1, whatever the position. So you just say xt plus 1 minus xt plus, minus whatever this whole term will do for a holonomic model. Vx delta t is actually to 0. So this is your constraint. Okay. So you have a constraint. And now one good important, one good interesting observation is that you can actually add this constraint to the cost function by something called a Lagrange multiplier. Why? Because if you want to minimize the goal, what happens is that whenever you are satisfying the constraint, you are directly, actually minimizing this cost function. We will always try to move in a direction which satisfies these constraints. How we do that, we'll just see how to do that. So this Lagrange function is actually useful whenever that constraint is satisfied. So we'll just go about solving that optimization problem. So when is the function actually at its stationary point, that is a maximum or minimum, when its gradient is 0. So we'll just consider the first order differential to the Lagrangian, and when you move along this differential, you should find that at this point of time there is you're not moving anywhere. That is basically it is zero. DL is zero, and then at that point you have reached a minima. So basically what we do is that you just expand DL because it's a function of two variables x and u. You will take dou L by dou x dx and dou L by dou u du, and this is actually called the Jacobian. Just one, I want to inquire that do you people know about Jacobian gradients, etc., etc.? I mean, all the optimization terminology. Can anybody answer? Hello? Hello?
Yes.
Yeah, I think we'll just conclude it pretty quickly. Looks like everybody is falling asleep. Cool. So one, take that gradient, and if you want to be at some minima, you have to ensure that this is zero. From this, you'll get a constraint for lambda, and similarly observe the changes in dx, for which you get dx in the variation in dx. You can just directly substitute that in the Lagrangian. And after you do all of these things, I'll give you this notebook. Whenever you're free, you can just read. And finally, you'll get to the conclusion that for you to reach some minima, or for you to be at some optimum at some point, you need to satisfy all these three criteria. Dou L by dou x is zero, dou L by dou u is zero, dou L by dou lambda is zero. Whenever you satisfy all those three things, you will actually be in something called a minima or a stationary point. One lucky thing for us is that MATLAB actually solves all of those things for you. So if you actually give an optimization problem, like the problem which we talked about previously. Let's say there's a robot here and it wants to reach some goal following some points. So the robot can take optimal actions by actually formulating this cost function like this. And if you want to follow a trajectory, we'll just put that cost function differently. We'll say that we need some V desired, and that we will always put our current velocity to be as close as possible to V desired. That will be a cost function. And if you are avoiding any collisions, you can similarly see that you can put your velocity to be as close as possible to the velocity you get from the collision cone, or you can also see that you will always avoid a collision whenever the Euclidean distance between you both is actually greater than that increased circle of radius r. So you can actually get this thing that you'll always have to be at a distance greater than r. So how do you do that? We'll take the square because it's easier. So x minus xo, x is your current position, and minus xo is their position, whole square, is actually greater than or equal to r square. You can see that you can put this as a constraint into this equation. So if you, after you do those two assignments, if you have time, you can actually sit and solve this equations with something called fmincon in MATLAB. So MATLAB has a function called fmincon which will do all of these things for you, and it will give you the optimal action. So your assignment would be to find Vx and Vy such that it satisfies these criteria. This is an online assignment. You can leave it if you don't want to do it. But the other two assignments are something which I'd recommend you to do. So I think I'll conclude now. So are there any questions? Um, if you people are having no questions, or then we can conclude. Cool. Okay. So now I think everybody of you can answer. After this lecture, how many of you think that you have got a basic idea of motion planning? Can you just say yes or no? Hello? Hello? I'm not getting any, not sure what to interpret. Cool. So these are the references. You'll find all the content which I gave here. So I'll upload this Berserker scribe to you people. It was actually written in the MR class. And you can see that Vivo equation from Vandenberg. And the time scaling is actually developed in our lab. So it's done by our previous PhD students, Arun. And optimal control, I would not ask you to go through this thing much. But if you want to, and if you're interested, you can read a book called Sirumos. And for the last problem is called something called model predictive control, for which you can read the paper of one of our lab students, Mithun. And there are other tons of work done in the lab by Bharat, Bhargav, and also me. So if you want to know anything more in motion planning, you're welcome. I think obviously this needs uh, some practice or something. So what I'm thinking is that I'll stop here, and tomorrow I'll forward this PPT to you people, and I want you people to at least solve by hand, numerically, or on a PC with MATLAB, and get some sort of results and verify it to yourself or with your peers, so that if you understood whatever is written, and if you do not understand, you can call me. So what should we do tomorrow? So should I come online tomorrow and clear any questions if you people have, or will the questions be emailed, or what should we do? What do you think is the best? Cool. If there is no
Can
answer,
you repeat that last sentence? I couldn't hear you.
okay. So what I'm saying is that do you? I know I wanted to solve this assignments. So if you can solve it either numerically by hand or on a PC, anything is okay for me. So the problem is, should I come here online after you attempt to solve these things, so that you can have some sort of doubt clarification or something, or will you mail the doubts to me so that you'll get your doubts clarified? uh, so what should we do? Should we come online, or can we just
So right now we have an assignment already that we have to submit in like I think 2
Mhm.
to 3 days. So everyone's busy doing that, I think. So I think the second option works better.
Okay, cool. We'll do that thing then. You just solve these things and get back to me whenever you have questions. So tomorrow is your assignment day. Yeah, that's the thing. Cool. We'll conclude the session, and I request all of you to drop, because Subodh said it'll get recorded if you do not drop. So everybody just drop the call. Thank you.